Thank you for all your help. Hi, thank you. I only arrived about 2 hours ago. So if what I'm saying is making no sense, I encourage you to, let me know that. I'm happy to answer questions as we go along. I thought I would show you, in great tradition, since you all like the pictures I showed of Dundee last time, a different picture of Scotland, and make a little plug for Matteo, who a lot of you know. He's organizing a UK Isaac Newton Institute math network on trying to make better models for peat, which is a porous material. I can't think of anything that's sort of more different than Saudi Arabia. Here's a picture of the flow country in the north of Scotland, where I was at with Matteo last week, and some peat scientists were showing us everything there is to know about peat. In this area, it's about 9 meters to 6 meters deep of peat. It's a very good carbon store, and they need better models and lots of uncertainty quantification because they want to say what happens when peat degrades. But for truth in advertising, that's actually what it looked like when we went, right? It is, again, 9 meters deep, and it's mostly water. It needs to stay saturated, and fortunately, Scotland provides. Right. So what I'm going to tell you about today is some joint work with Raoul and Christian, who you both know. And specifically, I'll tell you a little bit first about the rough Stein Stein model. So this is a linear rough volatility model. And then I will motivate and report our results, namely that the weak rate of convergence for the Euler scheme for these linear rough volatility models is h plus a half, which is better than it being h, right? And we'll see what that's about. And then I'll present the sketch of our proof, which involves making a Markovian extended state space and some Taylor expansions. Right. Is it not a picture of you? You're upset, Christian, about the picture? I need to update it. You could send me a new picture and I'll put it in.
You will.
Yeah, very good. Right. So linear rough volatility models. Probably a lot of people are familiar with these, and maybe there's some that are more familiar than I am. But rough stochastic volatility, right, is an increasingly popular paradigm in quantitative finance because it addresses 2 empirical challenges, right? So that's evidence based on realized volatility, namely that the time series that you see can indicate that the log realized variance has some hold irregularity h that's much smaller than a half, right? And the second is that you have this you're able to recover the power law explosion of at the money implied volatility skew that has this power law. So that's what you see here on the right in this very big plot, right? You see this power law type decay of the psi, right? So, right, the log realized variance behaves, right? The summary here is that it behaves like a fractional Brownian motion with some Hurst order h that's smaller than half, right? Typically, it's quite small, like say 0.1 or maybe 0.07, something like this, right? Fantastic, right? So how should we model that, right? Well, there's sort of 2 general classes of rough stochastic volatility models, right? One is the rough Heston. That's where this, so here we have at the top, I've put the equation for an asset price where here Z is some Brownian motion, right? And in the rough Heston case, right, the square root of this VT solves some Volterra SDE with a power law kernel, right? that's like r to the h minus a half. Okay. Another class, which I'll tell you more about, right, is this rough Stein Stein or linear rough volatility. That's where this VT is sort of an explicit function of some fractional Brownian motion. Okay, here specifically, the little arrow is moved, it should be pointing at the W here, the W H, right, is this Riemann-Liouville fractional Brownian motion, where we have this kernel K, right? Importantly, right, both of these classes of rough stochastic volatility models are not Markov processes, right? So right, that means, necessarily in the case where you're going to be looking at simulation-based methods, and simulations can be tricky, right? This non-Markovianity creates difficulties for both theory and numerics. Okay. So how is this related to the rough Bergomi model? Probably, I think I saw there was some talks about this, right? So, I mean, basically, right, you see here, again, for the rough Bergomi model, it's a slightly more complicated, right, explicit function of the fractional Brownian motion. So it's a little bit more related to the rough Stein Stein model than the rough Heston. And again, for this model, right, one needs simulation-based methods. Okay. So what can you do if you have simulation-based method? If you require simulation-based methods? So, right, essentially for rough Stein Stein and rough Bergomi, you have more or less an integral, right, like here. Of a fractional, of some function of a fractional Brownian motion, stochastic integral, right? It exists in the sort of classic Ito sense. Here we're going to assume that psi is some nice deterministic function. Since this stochastic integral exists in the classic Ito sense, strong convergence is sort of classical in some sense, and it's known to be rate h. Okay. Of course, we're going to be interested in the weak convergence, right? So this is expected values of some payoff function of our underlying asset, and then weak approximation, right, is often faster than the strong approximation. So what I'm trying to say here, right, if we were interested in weak convergence, right, and it was h, that would be bad. I have a slide on that next, but there's some hope in the back of our minds that maybe it won't be as bad as h, right? So, right, just to think a little bit about that, right? So, viability of numerics, right, would depend on the rate here, right? So if you have a small h, right, as I said, we suppose it to be, right? If you need n time steps to reach some error tolerance epsilon, then to reduce epsilon by a factor of 10, if h is 0.1, you'd need, 10 to the 10 time steps, right? You'd need to increase it by this factor, right? To get your error tolerance. And it's been observed, right, by Christian and Cheheb and Raoul that in fact it's probably not so bad, right? They didn't give a rate of convergence in this paper, but they did observe that for their particular problem, the rate was fairly stable, and they thought even enough to extrapolate it. So what's going on here? Well, when we started this work, Christian and had some strong opinions. He thought there was several plausible candidates for the weak rate. 2 to the h wouldn't make us very happy, right? 1 would make everyone very happy. That was sort of what they found when they were doing this extrapolation. Turns out it's not that good. It's somewhere in between, right? So it's not clear, right, what the relationship is between the weak and the strong rates in general for h is equal to a half, right? I mean, it could be, if we imagine this, h is a half, that would be a sort of classical Brownian motion. You could imagine it's like 2 times a half, or maybe it's a half plus a half, or maybe it's just 1, right? That was sort of what they were observing, right? So specifically, the convergence rate that we obtained was h plus a half, right? So this tells you that you can have viable numerical methods. It's not h, okay, importantly. So in general, right, this is the sort of result that we can give you, right? So if we have here some integral of a fractional Brownian motion, a stochastic integral of a fractional Brownian motion, where again WH is this Riemann-Liouville fractional Brownian motion for some h between 0 and a half. If you're thinking of sort of an implicit sort of Euler scheme here, this left point scheme with step size delta t, then we can tell you that the weak rate is h plus a half. Okay, but before I give some sense of the proof, I'll give some numerical evidence and ideas that sort of support the rate here, give you a little bit of a feel for it, right? So what have I plotted here? So I've plotted here on the left, this is sort of the weak error, right? The weak error for h is 0.05, and then here it's h is 0.15, okay? The weak error is computed with a sample, right, a reference sample that's much finer than these simulations. And the 2 different colors in each plot are a different observable. So here, this, payoff function, different community. Here the phi is x cubed in green, and here the phi is a heavy side, which isn't even really covered by the theory. But you can see what happens, right? So the weak error here, you get this slope, which is 0.67. Here it's 0.59. Here it's 0.82, and here it's 0.82. So, you can kind of understand the difficulty here, right? If you were to run these simulations and you don't know what the rate should be, right? And h is small, how do you distinguish h is 0.07, if the rate is actually h plus a half, okay, or 2h, right? I mean, this is a tricky thing, right? So what you can take from this, though, is that at least, right, this is consistent with, right, the rate increases as h increases, right? So here on the left we have 0.05, and here on the right we have 0.15, and we see that the slopes over here on the right. It's very heuristic to try and help you understand what you see when you're doing these sorts of simulations. Right, so as h increases, the rate increases, so it must depend on h somehow. And both of these seem to be generally consistent with h is plus a half, but it could also be some other, function of h plus a half. And, yeah, so it's consistent with that. Something I will mention, right, is this reference. One also needs to be quite careful, right, because if you choose your reference mesh, I mean, in a standard sort of numerical experiment that you might try, I don't think it's quite as important here if you don't sort of really overkill the reference mesh, because it's a sort of a rough path that you're simulating. You really see a pollution from the numerical errors. And since you're trying to discern something that's like h plus a half, sort of any little bit of pollution will tilt the line and make you think that the rate is very different from what you see. Okay. Here's I think, a very puzzling picture that we saw, okay? For this particular problem, the weak rate appears to depend on the payoff, okay? That doesn't happen, or at least it doesn't happen for, right, these non rough volatility. So what do we have here on the left? Okay, and the right, we both have a small h. Sorry, this is a typo. It should be, no, here it's small h, 0.05. And here it's 0.5. And for okay, sorry. So here there are two small h's, 0.05 and 0.15, that like we saw before, with a quadratic payoff function. And we see for both of these, right, we get slope that's around 1, okay, which is very different from what we saw in the last picture, right? I mean, when we had here a cubic polynomial and a Heaviside function, we don't get anywhere near 1. You put in a quadratic quadratic payoff, and you see a rate that's about 1, right? That's very puzzling. And then here on the right, we have for h is 1/2, which would sort of be your standard Brownian motion case. You can also get a rate close to 1. Here it's 0.9, and here it's 0.11 for other payoffs, okay? So what's going on here, right? I mean, this is quite surprising that the rate seems to depend on the payoff function. But sort of in the sketch of the proof that I'll show you, you can kind of see why this is happening, and that's kind of nice, I think, right? So sort of the way we'll make the proof, right, is to look at sort of these asymptotic expansions, and it'll immediately come out, right, what's happening with the payoff. Okay. The last sort of surprising, well, that last sort of heuristic graph I'll show you, right, before we look at the proof, is something that we tried after we sort of noticed this business with the quadratic payoffs. So we tried a shifted cubic. So instead of looking at the cubic, you shift the cubic a little bit, right? And that also gives you something close to 1 in the rate. So it really seems to be something happening funny with having a quadratic payoff versus other things, okay? So you see here that, even for very small h, this sort of shifted cubic is consistent with a rate 1. And it's certainly higher than just the straight cubic here. Here it was 0.6 and 0.82 for different values of h. And here, for both of them, it's right. And I think, this sort of numerical experiment is very interesting, because it really drives home the sort of subtlety of this problem of trying to figure out the convergence for this these linear rough stochastic volatility models, right? But altogether, I think, they can lead you to be optimistic that it's not h itself, right? So things aren't as bad as the strong error would maybe cause you to panic, right? It's not 2h, it's h plus a hat, right? Or something, okay? Right, so you should be optimistic that you can find sort of efficient numerical methods for a wide array of real-world problems where the sort of effective rate of convergence is maybe not as bad as the sort of theoretical rate. Okay, that was what I just said in words, right? So here's a sort of second theorem. I'm sorry, looks like it's crossed it out, but it was supposed to be underlined. Sending the slides to this laptop has done strange things to it, right? So here we can give a second sort of theorem, not sort of theorem, a second theorem, right? Where we say the weak rate depends on the payoff, okay? So if you have a quadratic payoff, then you find weak rate 1, which is, I think, very shocking, right? So if you've got the Euler scheme here, then you find rate one. That doesn't, I mean, if you're not so into the financial math stuff, that doesn't happen. Usually I'm much more excited about these things, but again, I left Scotland Saturday morning at 9:30, and I just got here 2 hours ago. So I've had coffee. There's not enough coffee in the world. Yes. Sorry, it just meant quadratic. Yeah. Yeah, that's a good question. So we notice with the shifted polynomial, right? So I think what it needs to be is that it needs to sort of be as viewed from the law, sort of. So not everywhere, I don't think. Just yeah, more or less. Yes. Yeah. It's a head scratcher, but we'll see. We'll see how it comes with the proof. I go till 3:30. Don't need 7 minutes, just 3:30. Yes. Right. So then what's the sketch of our proof, right? So again, this is a non-Markovian stochastic dynamics. And as is typical, right, we're going to try and write it down in sort of a Markovian extended state space and then use the only tool we seem to know in numerical analysis, which is Taylor expansions. But it's in some ways very satisfying. It's simple tools, but I think they're nice because they're a bit instructive and you can see what's happening, right? So then a general idea of the proof, right, is that we write down an affine representation for the fractional Brownian motion, okay? That's a sort of classical result. Then one approximates the affine representation, and this is this Markovian extended state space, right? So in theory, it's non-Markovian. You can write down this affine representation, but we'll sort of truncate it, okay? Then one writes down the discretization error as a telescoping series in the value function, and you can obtain rates by Taylor expanding and using conditional expectations. This idea of sort of looking at extended variable systems to facilitate analysis is something that's really common when people are looking at other non-Markovian stochastic dynamical systems like generalized Langevin equations, open Hamiltonian systems. So this is not like crazy stuff. It's sort of classical, but I think it's nice because the mechanism by which you sort of find rate one can be observed in the Taylor expansions, and that's nice. Right. So what do I mean when I say affine representation? So here on this axis, sort of coming out at you, right? You've got time, and here you've got theta. Yes. And what I've plotted here, right, is some y of t of theta, right? So this is I don't want to say old results because 1998 wasn't that long ago, I guess, but we'll say medium-term old results. Carmona and Katoon. So, right, we can say that this fractional Brownian motion, right, admits this representation as a family of these Ornstein-Uhlenbeck processes that are indexed by their mean reversion. Yeah, and sort of here you can sort of see this, right? So this axis is the theta. Here it's not so. This is nice and smooth in this direction, right? So the idea here is that replacing this integral, right, in theta, which is a nice smooth direction, with a quadrature rule, okay, allows in the parameter space, right, and then truncating it will allow us to project the fractional Brownian motion onto a finite state space. Yeah? Kind of the key picture, right? So we have the fractional Brownian motion. You can represent it as this family of Ornstein-Uhlenbeck processes. right? Where you sort of know what this constant is, okay? And then you're going to chop up this integral, right, with the quadrature rule. And that's where we get the sort of Markovian extended state space, okay? So is what I just said here, right? So essentially just a little bit of notation, right? So here I'll write S of y of t when it's important to think about the specific OU processes when we make expansions. And, you know, we have, oh, apologies. So this little hat was much more visible in my version. Sorry about that. It's a wee hat. Oh, a wee hat. I'm afraid. I guess PowerPoint doesn't know the wide hat command. I'm sorry. That'll make it tricky. So pretty much from now on, there'll be W's with hats on them. Okay. And what I mean by that is that it's this finite with NL degrees of freedom projection of the fractional Brownian motion onto these Markovian state space. So with these Ornstein-Uhlenbeck processes, right? Where again, theta here is this speed of mean reversion in the OU process. Okay, so you know we know this, right? That the WH here should have a hat is converging to this WH as you let NL get big. Those are sort of strong rates that Harms gave not too long ago. And just again pointing out here, sometimes we need to expand in actual OU processes. So we have just some notation for that. So if we split up the weak error, right, into the part here where we have, this is just a notation. I'm not saying that X is actually a function. Right? Remember, X was our integral of the fractional Brownian motion, stochastic integral. So here, this notation just means that it's right, that the full fractional Brownian motion, this is our WH hat, okay? So then this term in the weak error and this term, right, where we're looking at differences of the involving the fractional Brownian motion and the this approximate affine representation, these are controlled. The place where we need to find the rate, right, in delta t is this term here that involves, right, our numerical method. Okay. That's all this is saying. All right. So, what does one do then? Right. So now, if we have this approximate affine representation, okay, we have altogether an extended state space. Okay, and that's the dynamics that we want to consider, right? So you go from one equation to many equations, but at least this system is Markovian. That's the trade-off. Okay, so you have this Markovian dynamics in NL plus 1 dimensions, and you consider now your Euler discretization of that dynamics. And you can formulate a Kolmogorov backward equation, right? So that's this U function. And of course, right, you need to assume necessary regularity conditions on phi, right? It has to be sort of smooth and bounded. It's a matter of convenience, right? I don't think in the context of the problem that's a particularly strong assumption, but maybe Christian will yell at me if I'm saying something idiotic, right? Okay, so we have now our Kolmogorov backward equation for our payoff of our Markovian dynamics. Okay. Yes. Yeah. Yes. Oh.
Okay, so the dependence, right? So all these y's are driven by the same Brownian motion. Is that right?
Yes.
So one-dimensional Brownian motion drives all the y's, and that motion is independent of these w's.
This W
It's the same. Or?
Okay. So right. So this W with the H, right, and the W, is that
Yes.
what you're saying? Yes. Yes. They're separate.
Oh no, but you
Yes.
do the. Sorry, they're independent, or
yes.
the W is independent of the Brownian motion that drives all the y's.
Yes. Right. It's a stochastic integral of the WH.
No, it's the same.
Sorry,
it's the same.
same,
So you
yes.
drive everything with one-dimensional Brownian motion.
Yes.
All these n plus NL plus one factor. Okay.
Yes, yes.
Just to understand. It's fine. Thank you.
Yes. Sorry. Yes. Okay. So then what one does is we have a error representation, right, for the Kolmogorov backward equation, right? So you express, the increments of the Kolmogorov backward equation as a telescoping sequence of local errors, which is a pretty standard tool in numerical analysis. And then one can, right, so you look at this telescoping sequence in the value function, and you can, look at the local error using the Kolmogorov backward equation. That's what this is here, right? So this is just like one increment. And apologies, there's a little bit of notation here. So this involves increments of our OU processes in this sense, okay? And derivatives of the Kolmogorov backward equation, okay? All right, and this is sort of where you can sort of see why maybe the quadratic things are going to have a different rate, right? Because we have two derivatives of our Kolmogorov backward equations. Yes. And one can sort of imagine analyzing these. Apologies, this green line here should be underneath this derivatives. Yes. You can sort of just directly compute the fluxes, right? So you can imagine just exactly sort of deriving what this is, okay? And here is two derivatives of the phi of the payoff function, right? So if the payoff function is quadratic and you take two derivatives of it, you're not going to see these terms. Other things you will. Okay, and again, for this term here, you can also directly compute the fluxes. It's a little bit more complicated. These terms, these conditional expectation terms, I'm afraid we give them another name just to write down, because these are the terms that we'll want to expand in our Taylor series. Right, so that's what one does, right? Apologies, this is hard to read. So, right, we're going to Taylor expand, this new term and this, new tilde term at ZTI, and then apply sort of a conditioning argument. So, what does that look like, right? So, this Z bar, right, is linear over the increment from Ti to S. So what we want to do is Taylor expand the new, right, which was this conditional expectation, this guy here, right, in a Taylor series at ZS, okay, and then analyze the terms that are showing up in the series. a little tedious, but you can plug these expansions back into the local errors, and it all works out in the end, right? So the terms that are sort of containing these delta t's that you need to add up for the rate, right, are exactly these conditional expectations, these news that one Taylor expands. And again, I apologize, this is hard to read. Okay, so one difficulty, right, is that you isolate the order in the delta t using expansions, but one key argument, right, in the proof is that you need to show that the expansion coefficients are controlled with respect to the L theta, right? Remember, we replaced this with this approximate affine representation. We replaced an integral over d theta with a quadrature rule, right? Can tell you, it is a tricky argument. There are many times when we were lured into seeing rates that weren't real because we did not manage to control the theta, but in the end, we believe we did it. And I guess all of the referees did as well. Right. So, I mean, so the important thing here is, right, is that you need to sum over the thetas, right? In the end, you need to make sure you're not contributing any delta t, right? So that they, here I was just showing exactly that, a little taste of it. Apologies again, these tildes are very high. Right, so the finite expansion for quadratic payoffs, right, is exactly this, right, that sort of higher order terms here of nu and nu tilde in the expansions vanish when you have quadratic payoffs, which is what you're seeing. And then I suppose it's also why you're seeing the things that look sort of like quadratic payoffs to the function. Yeah. Okay. You can see, I mean, it's a lot of work. You need to sort of use some Lipschitz arguments, and for this case, you can compute covariance directly and get a very sharp bound on, including even what the coefficient is, right? You see here it's involving the time to the minus 2p, right? Where very importantly, p in our expansion was a number bigger than 2. So it's very touch and go, right? So since the p is bigger than 2, right, this term, right, will remain uniformly bounded when you go to sum over the TIs. Okay, so, right, returning to the telescoping representation of the weak error, if you have these quadratic payoffs, right, again, you have an error representation where you're looking at a telescoping increments of this Kolmogorov backward equation, right? You're going to sort of expand the conditional expectations nu in that's what these nu are in a Taylor series, and then be careful when you're controlling the thetas to get your rate. And for quadratic payoffs, it's honest to goodness, rate 1. Okay, and then more generally, one finds that the left point approximation to these rough stochastic integrals, right, converges with weak rate h plus a half. I'll make one remark. So Olgasat found a slightly better rate using Malevin calculus. but I think, I don't know, I still quite like the sort of expansions, and I like the constructivity of it, right? I mean, you can sort of see exactly what's going on here. Right, so the problem is very subtle, right? We obtain rate 1 for quadratic payoffs. So payoff functions well approximated by quadratic polynomials may be hard distinguished from rate 1, sort of empirically, I guess is the conjecture there. So that's sort of, when I say well approximated, I think what we were thinking here was sort of as seen from the law of the solution, right? We don't have a lower bound. Establishing the weak rate cannot be better than h plus 1/2 in general, and it would appear that it's probably 3h plus 1/2. Again, I think this is sort of really interesting, right? Because it's not typical that if you change the class of the regularity of the payoff, then you see a different rate. So something very interesting is happening with these rough stochastic volatility models, right? Imagine you're doing some other problem and you compare two polynomials and you see a different rate. That would be a very strange thing indeed, I think. Okay. So what did the proof look like? Just to remind you, right? So for the left point scheme, we find weak rate h plus 1/2 for general payoffs, but weak rate 1 for quadratic payoffs. The proof relies on, well, our proof relies on Taylor expansions and an affine Markovian representation of the underlying. And then from these asymptotic expansions, you can sort of observe the mechanism behind the different rates, for example, for quadratic payoffs. Could it be extended to sort of a more general psi? Possibly, but we've not done that, and I don't know. I think slightly more interesting is the following question, which is if you have sort of this model and other models, is maybe to ask questions about sort of Bayesian model selection, maybe even averaging. So this sort of linear rough volatility and rough Bergomi models, and one could imagine they have k-factor Bergomi models and all sorts of things, and it would be interesting to sort of know among those zoos of models, maybe which are supported by the data, which ones have stronger evidence than others. And that's something that Christian and I are working with Eduardo on. Right. Thank you for listening.